So thank you everyone for joining today. I want to welcome everyone from the Rise Hub and our SURE students as well. So today presenting, we have Dr. John Kline from Los Alamos National Labs. He is currently the program manager of the Fusion Energy Sciences program. Um, John loves talking about fusion altogether. And if you guys have questions, he is more than happy to answer any of them. So please do not be shy. He's an expert in modeling a lot of our target physics, and I'm excited to hear him speak. Is there anything else you'd like to add, John?
No, expert's a strong word. No, I know a little bit, yes. Um, Hopefully, thanks for the introduction. As Kavita said, I'm John Kline. I'm heading as part of our RISE Hub Thrust 1, which is target design. I've actually been learning a lot more about it. I thought I knew more about it until, you never know how much you know about something until you do it. So as I have been doing, I have been learning as well. I have tried to organize. I'm actually been giving this talk for a couple of years now, trying to work on it. I'm actually happy with this version. I am going to try to lay the theme for design, but we won't talk a lot about the design of the capsules because I'm very passionate in the fact that you have to understand the basics, and for all fusion systems, understanding how the power balance works is really, really fundamental and really important. And as I do that, I'm going to tie it to things that are important for laser fusion. So we'll see how this works. As Kavita pointed out, we're all part of the RISE Hub, which is part of the IFE funding that comes from the Office of Science, Fusion Energy Sciences. And our collaboration connects with private companies like Marvel and Exemer, laboratories, Naval Research Laboratory, SLAC, and then also universities. So this is a good way to advance any field when you take the best of each of these sectors and put them all together. So I'm happy to be part of this RISE Hub being funded from FES. I think, as I said, understanding the fundamental aspects of fusion provides the physics framework you need to kind of evaluate these things and understand what's going on. What we will talk about, and I've rearranged this a little bit, but what are the important pieces of physics that go into getting an ICF capsule into a burning plasma regime, which is really important if you want to do fusion energy. And I'm going to talk about those basic key aspects. And the last one is kind of an obvious statement now, but for fusion, what we want to do is press isotopes of hydrogen, mostly deuterium and tritium, to get fusion out. And hopefully, as we go through this presentation, that'll be clear as to why, and then also how we have to do it, and what on time scales we need to do it on. So one thing is, which is really interesting, my background is actually plasma physics. I came from low temperature plasma physics as my graduate work. But plasmas are really interesting because plasma density and plasma temperature span all kinds of different plasmas, going from looking at ionospheric plasmas like the aurora. If you've been watching the news lately, there have been several days where the aurora borealis can be viewed well down into the mid United States, which is kind of interesting in itself. There's solar plasmas, the solar wind. That's a source of a lot of investigation because the sun puts off coronal mass ejections, which ejects plasma out into the solar wind. Those solar wind particles hit our satellites and stuff like that. So there's a lot of interest in that. Then there is your fluorescent lights and all kinds of lighting things, which is in another regime that's important. Then there's fusion plasmas, which actually span a range of densities going from 10 to the 16 particles per cubic centimeter up to 10 to the 22, which is a big range of densities. And then we also span a wide range of temperatures from 11,000 Kelvin up to many millions of Kelvin, right? And as you're in each of these different regimes, the plasma behaviors which dominate how the physics that dominates the plasma behaviors are changing. So if you're thinking about a fusion plasma, you're not going to get the same physics as if you're thinking about space plasmas, because what's important in each of those regime changes. So it's a complex field. When you're sitting in talks a lot of times you're like, that's wrong, and then you have to remind yourself, oh, wait a minute, that plasma is in a different regime. So plasmas in general are really interesting as a whole, and these are ionized gases, and we're going to use them in the high density, high temperature regime. So starting with fusion, I think what's really important is to understand your fusion reaction rate. You know, what do you have to do to get a fusion? In this case, I'm going to talk, I'm looking at the equation up on the upper left-hand side, because for most of our plasmas that we'll talk about, you're going to have some deuterium and tritium atoms of a given density in a plasma. And then they're going to have some temperature. And what we do is we have this probability of a fusion event that we fold into what we call a cross-section. And that cross-section, what we do is we look at the likelihood of a collision given integrated over a Maxwellian distribution. And depending on the density and the temperature or the cross-section, you will get a fusion event. And the rate of these fusion events depends on this equation. And it's also important to realize that the cross-section is an average, so it's actually a probability. So just because a deuterium and tritium kind of collide, that doesn't mean they're going to fuse. So there is, you know, these things sometimes bounce around a little bit before they actually fuse. So the thing in this equation now that you go, well, where all the physics is hidden is in this cross-section term. And that cross-section term, like I said, goes as kind of this cross-section. Here I'm showing it in meters squared. And I'm looking at the center of mass energy. This is basically, if I take two particles coming at each other with different masses, I can go to the center of mass frame and I can look at the relative energy in keV between them. And this gives me the cross-section. And what you can see is the blue line is the deuterium-tritium cross-section, which you can see that that cross-section occurs at a lower energy and is higher than all the other fusion cross-sections between other particles like deuterium DE helium-3, proton boron, which you'll see people often love to talk about because it's, you know, it doesn't produce any neutrons, so it's aneutronic, so it's cleaner. But, you know, if you look at it, your plasma, you know, temperatures or your center of mass energy is, you know, it's way up there. You're going from 5 keV up to close to 100 keV in order to make that happen, which means you have a lot more energy in your plasma. So this is fundamentally why deuterium-tritium is always preferred fuel, at least to start with. There are other schemes that are looking at using some of these other reactions, but as you can see, they're going to be much harder than deuterium-tritium. So if you can't do deuterium-tritium, you're probably not going to do p-boron 11. And this is why. And this cross-section basically gives you the probability of fusion. So this is essentially the fundamentals. And what this means is if I put some deuterium and tritium in a hot enough gas that it's ionized, fully ionized, which is going to, you know, for deuterium, you know, 13, it's, you know, 50 EV should be enough to get deuterium and tritium kind of fully ionized, and, you know, I will get fusion out of this. But usually the fusion that I get out, the rate at which it occurs is so slow that the energy that I have to put into any kind of confinement scheme, a magnetic field, an electrostatic field, or anything like that, that energy is going to be more than the amount of energy coming out in these fusion. I mean, the power is going to be not there. So while this equation tells you something about the fusion rate, we will get to the more important thing, and that's power. Now, these cross sections, as you see, the center of mass cross sections go up rapidly as you go above 5 keV. So this means that if we take another look at where the fusions look at, and on the right here, I'm plotting energy in the plasma versus the relative probability of the fusion, you can see that there is a crossover between the cross section, which is this curve here, and the energy in the particles given a temperature. And as I said, this cross section goes as an integral of that. But what you're seeing is that most fusion is going to happen out on the tail. So even though I'm going to say, well, this cross section goes as the temperature of the plasma to the fourth power, most of the fusion is going to happen in the high energy particles, not the bulk of the particles. And that's just something to keep in mind, because a lot of times, as you see, we'll talk about the triple product. We'll talk about it in terms of temperature because we like that term, but it's really the tail that matters. This is just to make sure that you realize, because of this cross section, that if I have a 1 keV plasma, only the 1% of particles out on the tail are going to have high probability of fusing, right? That gets lost often, so I just wanted to make sure people were aware of that. And this idea of the gamma peak, if you go out and you're interested in reading more, you should make sure you look into that, because it is important that it's not just all of these particles that are playing a role in the fusion, it's the ones on the tail. However, if I go back and look at this equation, I have density, I have cross-section, which I'm going to refer to as temperature, because as the temperature goes up, I do get more fusion, and that's because I get more particles on the tail. And I have this power, the number of fusions per time. And I should have written it down explicitly here, but this N tau T, which is temperature, are the three terms that we often refer to as a triple product. And now you can use this triple product to get some information about the relative, how good one system is working to the other one relatively, right? It's not a perfect measure. So just because something has a high N tau T doesn't mean it's going to be turned into a fusion energy source anytime soon, because it still has to cross the threshold for a burning plasma. And but it is kind of a measure, and the reason it is there is it basically tells you what the fusion rate is. The density, temperature, and then how how long the energy is confined. You can get some idea of how many fusion products you're getting out of this. And there's a paper by Sam Wurtzel and Scott Chu where they use this kind of metric to compare all fusion things. So this lets you compare laser fusion to magnetically confined fusion to other schemes and where they are, and then you can go through here and look at the different plasma devices or facilities out there and kind of look where they fit relative to each other. So this is kind of a good measure, and you can tie it back to the fact that this equation tells you what your fusion rate is going to be. Now, as I said, the fusion rate is an important equation because it's a rate equation, and it really puts us in the regime we really care about, because it's power. Because putting energy on the grid is about power. It's not about how many fusion events you happen. It's about the rate at which you have these fusion events, because the neutrons are going to be used to heat water, and if you have one neutron hitting your in your power plant, hitting your water every day, you're not going to get a lot out of that. It's not going to heat the water. So it's about power. And now I am going to switch here. I'm going to come back and tie this into other schemes later, but I'm switching directly to thinking about lasers. And in lasers, we could think about, what we do is we compress the DT fuel, and that is what we call PDV work. That's pressure times the change in volume. So I start with a certain amount of DT. It's sitting in a capsule. I heat it with the laser, or I use a magnetic field from, say, a Z pinch or something like that. I then compress that plasma, and that's PDV work. And what that does is that gives you density and temperature, and then there's going to be some confinement time. And as that's happening, I'm going to have losses of energy, radiation and conduction. This is going to determine what temperature I can get to and what my fusion rate is. Now, for a laser plasma, this PDV work is not enough for us to actually get a compression. So one thing is, you could think, looking at my capsule on the right, I could take a capsule, which is an ablator. I could put some DT fuel in it, and I can just compress it and heat it, right? All at once, and try to get energy out. And this is what I would refer to as kind of a volumetric burn. But on the left, I can do some quick calculations. If I want to get an amount of fuel that I need, which is 150 micrograms of DT, and I want to get it up to 5 keV, I can then figure out how much energy it takes to compress it and heat it to 5 keV. I mean, I can just look at the number density times that. And basically what I find is, in order to get this thing up to 5 keV, which I would need to try to burn a significant fraction of the fuel, all of a sudden I look, I'm going to need a 60 megajoule drive. I need 60 megajoules of energy to be able to get this thing to fuse enough to make it practical if I just use PDV work. Obviously, that is not a very good way to go if you're trying to make an energy source. And NIF is not enough energy to do volumetric burn. So luckily, we have this other source of heating called alpha heating. What that is as I probably didn't talk about as much because I made a little bit of assumption that most people are familiar, but we're taking isotopes of deuterium and tritium, and when we fuse them, we get a neutron out, which is what we're going to use to heat water and then drive a turbine for power systems. But we also get this helium at nucleus at 3.5 MeV. Well, the mean free path of that, if we're dense enough, is short enough that we can actually capture that alpha particle. And if we capture that alpha particle and we have a high, reaction rate here, that is, 3.5 MeV is a lot of energy, right? So now we can actually use it to heat the deuterium tritium fuel. And in this case, I can take a small amount of, let me go here first. Just to set the stage to make what I'm doing a little bit better. If we're doing ICF capsule, what we usually do is we put an ablator, we put a layer of DT ice, and then there's this residual low density gas on the inside. And as we compress this low energy gas gets compressed to the point, because it's a small amount, we use it to heat that up, start getting fusions going, and then we use that to actually use the alphas to burn the DT gas. So with that, this is what we call hotspot ignition. And in there, we have a small amount of gas. Its density is much lower, but we can get that to 5 keV. We can get that burning and producing alpha particles, and then we can use those alpha particles then to burn into this cold, dense ice layer and burn propagate into it. And then now we only need, 1 or 2 megajoules of a driver. And this is how NIF was able to achieve getting more energy out than I, is they use this hotspot idea, and they require the alpha particle power to be able to get us into a regime to do a burning plasma. And what that looks like is something that we refer to as the Lawson criteria. So the Lawson criteria is the minimum amount. This is the threshold where you need to get to where you can start getting significant enough where your energy into the DT gas is greater than your losses. And what that means is you have PDV work, which is over here. That gets you started by compressing and getting some temperature into the plasma. It gets you to a point where you start to get enough alpha particles that the alpha particles can take over. And between those two things, the energy going into the DT gas is greater than your heat conduction loss and your radiation losses, at which point in time you can get to a burning plasma. This is when the alpha heating takes over and the temperature of the plasma goes wild, and you quickly raise the temperature. Your cross section, as we talked about, goes up. Then you get you burn up a lot of the fuel, and you get, many megajoules out of the plasma with only putting a few megajoules in, right? And that's what you need to do. And this condition that you have to surpass, we refer to is the Lawson criteria. Then you worry about the confinement time. It has to confinement time. And in our case, the confinement time is after you start heating this up, the pressure of the hotspot then wants to push the ablator out, at which point in time you start to disassemble, and the fusion reaction will decay away. So you have to do all of this stuff in that amount of confinement time. And that's why it's called inertial confinement fusion, because it's done on the inertial time scales. So the initial Lawson criteria will be this dashed line that you have to get above. But as this thing starts to disassemble, in order for the PDV term actually turns negative. It's positive during the compression, but as it starts to expand, it turns negative. And then the alpha heating term is your only heating term, and slowly this thing disassembles. And like I said, this is kind of a complex thing. Normally, people will just talk about the dashed line, but I think it's also good to think about the disassembly, because the disassembly will set your confinement time. And all of these things are coupled, so you can't get rid of one without the other. So PDV is positive then negative, and when it starts to go negative, and all of a sudden your density and temperature start to decrease, and your alpha heating can no longer is no longer greater than these losses, that's when the fusion system is considered disassembled, and you're no longer going to be getting a lot of fusion energy out, because that's when your burn is starting to go away. So that's kind of how this works, and the Lawson criteria. And if you notice, I write the Lawson criteria in terms of this triple product: density, ion temperature, confinement time. And this goes back to the plot I showed you of how you can kind of compare different systems relative to each other and where they are in terms of being able to produce energy out.
John? John,
yes.
Quick question.
Yes.
What is CS,
yes.
C sub S in the confinement time?
Which, say that again?
The capital C sub S, what is that term?
Oh, I'm sorry. That's the sound speed.
Okay, thank you.
So if most people write the confinement time as so if I compress something and then I let it go, it usually is the sound wave that's crossing the material, and the radius of the material will tell you how long it is confined. But I should go back and update this slide, because as I just said, that is partially true. That is the maximum confinement time. But as you build up pressure in the center of the capsule, that pressure becomes a force, which will also start to push, make the hotspot bigger, because the pressure will start to go out. Density will decrease, temperature will decrease, and you'll start to fail there as well. But usually we think of as a rough first estimate, it's a sound speed crossing time for this.
Thank you.
Yep. So now if you want to understand, hopefully we've gone back, we've talked about you got to get this fusion reactions, which depend on density and temperature. Your confinement time and how much you heat them, takes the dNdt and puts it into power because you have a certain amount of confinement time. It gets you to the triple product. Now you're looking at power balance, and we've talked about that if you just had PDV and no alpha heating, you probably would need too much energy to overcome this reaction rate because you would need a huge driver. And then we've talked about how the alpha heating actually comes in and saves the day. Usually nature's not beneficial, but in this case, it provides you a way to get out of it. But you still have to beat this Lawson criteria. So, what you now do, once you understand that, the next level of physics is what is the physics in each of these terms that we have to understand. And in PDV work, we start out with this big laser. And for ignition, we put it into a gold can, and I'll talk about the different types there. That ends up meaning less, there's an efficiency there that you lose energy compared to what goes into the capsule. And then the capsule compresses the fuel, in which case the amount of energy you get in the fuel, there's another efficiency term there. So you have to think about whatever driver you have, how much energy you're getting to the fuel, whether it's direct drive or indirect drive. So in terms of this PDV work, how much goes into this is actually how much you can actually get coupled to the fuel. Then once you assemble the target, you have radiation losses and conduction losses. And then the last thing we'll talk about is 3D effects, which also lead to compression and efficiencies. So now the physics that we're going to talk about is going to be tied up in these terms. I'm not going to talk about the conduction losses. They happen at high temperatures. And for our systems, they're definitely play a role, but they're not the important term. The radiation loss is the important term. So now, how do we do this? So for inertial confinement fusion, which we'll focus on, we have, as I said, an ablator. You have a layer of thick, DT ice, which is, your fuel layer, and then your residual gas. You compress this on NIF. We compress this by a factor of 30. With direct drive, because you don't have to, because you have a lot more energy, you don't have to go. You can couple more energy with the systems we have today. You don't have to go this far, but this ice layer gets up to densities of 400 to 1,000 grams per cc. So this is very, very, very dense layer. We refer to the residual gas as a gas, but it actually gets compressed to about 50 grams per cc, which is greater than solid density. But compared to the outer side, it is a gas, right? So be careful. Since it starts out as a gas, we call it a gas, but it really gets compressed to a very high density as well. And now we have to get these to 5 keV to get the cross section to work, which means we have pressures from 100 to 400 gigabars inside these systems, right? And we converge them, which, as we'll say, means that they're relatively unstable. And then how we do this is we ablate the material on the outside, we compress it, we heat it, we get it to burn, and then it explodes. And the explosion phase, that will also play a role in the confinement time, as I said. But the PDV work, how do we get PDV work? This is something you can look at as a simple rocket equation. The outside material gets blown off of the ablator, right? It comes off at a certain velocity. And that then leads to an inward force, like the rocket equation. Some of this stuff is a little, I could have started off with the different dm dt times the velocity it comes off with. But this kind of gets you closer to the solution that you can work, and you can find the velocity of the shell comes off as the mass on the pressure of the ablation over the rate of mass being thing times the log of the initial mass to the final mass. And this tells you, basically it looks at this rocket equation. And then over here, this picture kind of shows you that going in. The blue is the ablator. These lines coming off are in kind of Lagrangian units. And what you're seeing is they're being ablated off. And as they're being ablated off, they compress this gas, which is the red gas on the inside, down to this maximum compression, heating everything, and then you get the diffusion burn. So basically, this is how the PDV work term occurs. But as I pointed out to you before, once it gets compressed, as this starts to get hot, it starts to have a pressure pushing back, and then the PDV work of the gas on the remaining ablator material starts to then become a sink, and the density starts to go down, and the temperature will start to go down, and at some point in time you'll quit burning, right? So the burning plasma regime where you're getting all your fusion out is just over this small region of time, which is kind of the inertial time. But this is how you do your PDV work on capsules. So that's the PDV term. As I said, there are two ways that we often do this. On the left, we call direct drive, where you shine the lasers directly onto the capsule and you ablate the material off. And on the right is what we call indirect drive, and that is when you let the laser shine into a gold can called a hologram. The laser energy hitting the gold can creates X-rays, and then those X-rays then compress the capsule. These different ways have different advantages and different disadvantages. In the laser drive, what happens is the laser, once the plasma density outside the capsule goes up, there's something called the critical surface. The laser penetration can only penetrate to the critical surface, and as the plasma blow off increases, the distance between that surface and the ablation surface increases, which means the efficiency of your drive or your ablation drive, it becomes less. However, because you can couple more energy, because you're coupling all the laser energy, the 1 megajoule or 1.2 megajoules on this, you kind of overcome that a little bit because you couple more energy to the target directly. But there are other instabilities and non-uniformities and hot electrons and LPI, which come into play there, which I'm not going to talk about in this lecture, that make this choice, a trade-off. You get more energy in the capsule, but you also have to overcome these other 3D effects. On the other side, X-rays are really nice because X-rays can penetrate deep to the ablation surface, get you very high ablation pressure so that you can drive this capsule in. But when you go into this gold hologram, you basically take the 2 megajoules of laser energy and you only couple about 250 kilojoules into the capsule. So over on the left, I might be able to couple 2 megajoules into the capsule, but I have these problems. On the right, I get better coupling to the capsule, but I've thrown away 75% of my energy to convert it to X-rays. So if I had a 10 megajoule laser or a bigger laser, then the right makes a lot more sense. If and even on the NIF at 2 megajoules, it makes sense. But in principle, with 500 kilojoules or 750 kilojoules, I could get fusion out if I use direct drive, but I need 2 megajoules on NIF with indirect drive. But we've never done these at a big enough scale to show that we can overcome all of these other effects that don't scale. So right now, we know this works, but this is the trade-off between direct drive and indirect drive. So for IFE, for fusion energy, right now I think people are thinking more about direct drive, because you can couple more energy directly to the target. With indirect drive, you have to make a bigger driver, although people are thinking about that as well. But these targets are also more complex. So for IFE, there are still trade-offs, and looking at the direct drive is something that our hub is doing for this. So which method to go for energy, I don't think has been settled yet, because you're still trading off target complexity. You're going to have to fire once a second. You're going to have to build these targets on the right, even though we know that they might be more advantageous for getting to ignition. But if we work on the one on the left, the direct drive has still kind of got its advantages as well, because it might not be as efficient because of the laser coupling of energy to the target, but I can couple more energy directly to the target with the laser. So this is still a up in the air question, but these are the ways that we typically use a couple to do our PDB work. So what we deal with most in plasmas, and this is true for magnetic fusion energy as well as inertial confinement fusion, is in a plasma, it's different than having just a regular gas. Because you're looking at charged particles, and those charged particles colliding, what happens is you get an acceleration. And if you, in your electricity and magnetism class, you find that when you accelerate a particle, that particle emits electromagnetic energy. So now if I have these two particles, in this case, I'm looking at an ion and an electron, as that electron starts to come close to that ion and it starts to deflect because the electrostatic force between, oh, actually, I should be careful. In this case, I'm showing an ion and an ion because it's being repelled. An electron trajectory would be the same. It would just be trying to go towards the ion. But in any case, these things radiate. And when they radiate, that means they lose energy. So that is the biggest source of your plasma temperature. And as we showed, plasma temperature is a key fact to getting fusion. And here up on the upper right, I'm showing you power and Bremsstrahlung is not the ion-ion density, but the ion-electron density, and the temperature to the 1/2 power. As the temperature of the plasma goes up, you basically see that the radiated power kind of clamps. I mean, it's going to go to a kind of it's going to asymptote to a fixed number as long as the density is fixed. And this just kind of illustrates that in a little bit better way, that if I had just a regular gas on the left and a plasma on the right, and let's say that for argument in this thought experiment, that the walls of the box are insulating to mechanical changes, but absorb radiation. That my ionized gas temperature, once I fix it in the box, it'll stay at that temperature, which is the green line. But the plasma, as it collides and radiates and the energy gets absorbed in this box, the temperature of the plasma is going to go down, which means if we're talking about fusion, that means the fusion rate is going to go down. So this is really important, and why the fusion plasmas and why fusion is hard is it mostly comes to do with we actually have losses that cause the fusion power to go down as a function of time. And so for inertial confinement fusion means we have to get this thing fusing and heating very fast and try to get as much out as we can over a very short period of the inertial confinement time. So with that, going back to our alpha heating, it's the fact that we have these radiative losses, but we have the alpha heating in to overcome these radiative losses. And how that works, you can take the inverse, the Bremsstrahlung power, and then look at the alpha heating power, and you can see that at some point in time, as you go up in density, the alpha heating power overcomes the inverse Bremsstrahlung power. So your heating rate is faster than your cooling rate in what you're doing. that is essentially this line right here. So as you go up in density at some point in time and temperature, down here, you're dominated by Bremsstrahlung losses. As you get to a point right here, basically the alpha heating power above 5 keV starts to dominate and the Bremsstrahlung dies. And that's why you see, as you go up in density, you basically see that the threshold doesn't change very much. I just actually figured that out. I've always known that because I've been told that, but I only just understood it today. Just so you know, life is always about learning. Just because I might be doing this for a long time doesn't mean I know everything. So one of the things that I had put in here is 3D effects, because I'm not going to talk about them because the lecture was short. But as you try to compress these capsules, this is a picture from Dan Clark from 3D calculation. This is what a hotspot looks like. And you can see this was for a CH target where the tent scars, the fill tube, the surface of the thing all lead to these 3D effects, which means you don't have this perfect, nice, round hotspot. And that also means that the energy you're coupling from your laser is not going into heating the fuel. So that's also considered a loss. But as NIF moved forward, this was the main lever that they used to actually get into an ignition regime, is they minimized the 3D losses. This means they made rounder implosions. They were able to, they thickened up the shell, which means you need more driver energy, and they coupled more driver energy, but it meant that features like this pushing into the hotspot didn't occur, which means the hotspot maintained its integrity. And then also, if you start to push some of your carbon or your ablator material into your hotspot, if you look at your Bremsstrahlung equation, there's this Z here, which means higher Z materials radiate more. So if you get carbon into your hotspot, it's going to radiate more than just a deuterium and tritium. So they were able to control these 3D features better, which allowed them to get rid of that loss term so that they only had to deal with the losses due to radiation of the deuterium tritium. They were able to drive the implosions faster so that they were able to heat the capsules up faster than the losses. And that enabled them to get into a regime where they're now able to get 32 times the amount of energy absorbed by the capsule out of the capsules. Now that's only 4 times the laser, but as I said, the laser loses efficiency in indirect drive. You throw away 75% of the energy in converting to X-rays, so that's a little bit of an unfair gain. But when we talk about IFE, if you choose to go with indirect drive, while the comparison might not be so fair, you will have to overcome that for your power plant wall plug efficiency. That's why that's going to be a hard direction to go for indirect drive, is because you're throwing away a lot of laser energy to get you there, where direct drive might be a better option, although it has not been demonstrated yet. So hopefully, going back to this, this power balance picture is really important for any fusion system. You have to get to the point for most of these, for laboratory fusion, where your alpha heating rate, the heating that you get from your alphas or other sources, is outpacing your loss rate, so that you can maintain a burning plasma, which is where your alpha particles are actually playing a role in heating your plasma. You're taking advantage of the fusion energy, not only the neutrons coming out, but the alpha particles to serve as one of your heating mechanisms, because that's the only way a practical fusion energy is going to occur, no matter what the system is. Now, getting fusion, as I stated from the beginning, you can do it purely with PDV work if you had a big enough driver. But those drivers are not going to be practical for fusion energy or practical in the laboratory because no one's going to build a 60 megajoule laser. Well, at least not anytime soon. But there are other ways to kind of change this Lawson criteria of where, what temperatures or what densities you need to get to. On the right, if you're going to do burn propagation or hotspot ignition, you're going to have to be in this blue regime. But there's also these volume burn regimes where are not going to be necessarily for fusion energy because you're not going to be able to burn enough fuel. But we are working at Los Alamos on double shells where we use a low Z material to come in. It collides with a high Z material and compresses the gas, and we get into a fusion regime. And for that, we can actually lower the temperature because in this case, we can put a high Z material around this, and we can reduce the inverse Bremsstrahlung losses. I mean, the Bremsstrahlung losses. However, in order to do this, we have to lower the amount of fuel that we can heat. When I first showed you the calculation for 60 megajoules, that was with a practical amount of fuel to get a lot of energy out. But if, let's say, I only want to get 1 megajoule of fusion energy out, which is less than my laser in, and I don't care, in this case, I can lower the amount of fuel that I put into this thing and only burn a smaller amount of fuel because now, instead of 150 micrograms, I can go with 10 micrograms. That means I need 15 less. My driver needs to be energy coupled to the fuel has to be a factor of 15 less. I divide my 60 by 15, and now I'm at a 4 megajoule laser, right? So, but like I said, it's not practical for fusion energy. The other thing you can do is you can use magnetic fusion. This upper left is a maglev design where they use a magnetic field to compress this from a Z-pinch motion. They heat up some of the fuel in there. And then what happens here is the magnetic field will confine the ions because they're going to be contained to the magnet or the field lines. They're going to go into a gyro motion. It's going to do some temperature confinement, and that will let you go to lower densities, but slightly higher temperatures. So you can actually change the regime and the Lawson criteria you need by going to these other things. But again, this is a pulse power system. To pulse power systems, I don't know how we're going to reparate that for inertial fusion energy. But part of what I want to convey here is even though we're kind of focusing this on fusion energy, I want you to get a sense of the power balance, and that if I change things like the energy confinement time, I can change the threshold of the Lawson criteria. Now that might not be practical for energy, but if you want to do other applications where you want to understand nuclear physics or try to do other things, there might be other regimes where you can get away with, getting fusion in different regimes of density and temperature than what we would need for inertial fusion energy. And I'm going to come back to that. So with that, I think it's important also to not just understand I focused on inertial confinement, but if I'm going to do magnetic confinement or even the sun, the principles of power balance or the triple product are the same. This is really important because if you're sitting at a meeting and you go to a plasma physics meeting or you go to a magnetized fusion energy meeting or something like that, using like in most physics, if you think about your conservation laws or your power laws or things like that, you can actually understand a lot without maybe understanding the details of the physics of the terms that we just went through, like Bremsstrahlung. So for inertial confinement, your DT, your confinement time is small. So in order for this to really work, we need high densities to get us there. And that's why we use the lasers to compress things to high densities. If we were to move to, say, a tokamak or another fusion device, here what they do is they use a magnetic field to confine the particles, because the particles, a charged particle in a magnetic field does a helical motion, which means it can't go to the wall, so it actually gets confined in the plasma. So in that case, what they do is they take the tau, or the T, they make T a microsecond versus 100 picoseconds, in which case the density can go down by 5 or 6 orders of magnitude. Now, the dominant mechanism of loss, they do have radiant losses, but one of the dominant loss mechanisms they have is the actual particles collide, and they will actually make it to the wall. And if a particle leaves the plasma, that's an energy loss mechanism. So they're often refueling the plasma to do this. But because their stuff takes place on microsecond time frames, if you go to a magnetic fusion energy talk, you'll hear them talk about, ion cyclotron resonant heating, neutral beam heating, other heating mechanisms. Their stuff happens on such time scales that instead of just alpha particle heating, they can put in other heating mechanisms as source terms to help them maintain their plasma. Nonetheless, that might add another term to this equation, but this power balance equation still holds, and they still have to get to the same n tau t's. And for the sun, basically tau, because of gravitational confinement, goes way up, right? And in fact, the sun does proton-proton fusion, which the cross sections are like 10 to the minus 31. I mean, they're really, really tiny. And the reason it can do it is because the confinement times are infinite and the scales are large, but it's still about n tau t. So looking at this, what you tend to happen is as you move to the right, except for the sun is an anomaly, but as you move to the right from inertial to magnetic fusion, you increase confinement time and you decrease density, but it's all power balance. So, so you should be able to always be thinking about this. If you're sitting in a talk and somebody is talking about something and they talk about, look at their temperatures and densities and they want to do something, if they're not able to, magnetic fusion energy has not gotten to a burning plasma yet, a place where their alpha particle heating is dominating their heating mechanisms or is greater than their loss mechanisms. And they haven't gotten to the point where they can produce more energy than they put into the plasma yet, because they still have to work on their n tau t. So one last concept that I would like to point out in terms of inertial confinement is this idea of fuel burnup fraction. So for inertial confinement fusion, you're going to have a capsule in it. It's going to have 150, 200 micrograms of deuterium and tritium in it. When you fire this, you want to burn up as much as possible, because the more DT fuses, the more energy you get out. So that burnup fraction is another really important quantity to look at for inertial fusion energy. And if you start with the equation that we initially talked about here, the fusion rate, you can take the DT and move it to the right side. You can take the density terms and rewrite them as a single density, because you know it's half deuterium and half tritium, and you know that you need one of each to fuse. So that you can then make this dN over N is equal to the cross section times dt. And if you integrate this, you can get an equation that looks something like this, where you have what I'm going to call is the burnup, or this phi, which is the number of fusions over the initial density, which is a burnup fraction that looks like phi over 1 minus phi is equal to the initial density. And since T is over here with just the cross section, it's just a tau, and you make that your energy confinement time. You can rewrite this in a couple different ways. If I assume my confinement time is this radius over CS, which is the sound speed that we talked about before, I can rewrite this as rho r over rho r plus This is only for DT. The other cross sections, the 6 grams per centimeter squared would change. The areal density would change. But this basically says, so you'll hear people refer to rho R, which is the areal density, right? Because density is density over cubic centimeters. If I multiply it by R, it's over square centimeters. So it's basically tells you something about the density as a function of area going out. You will hear people talk to, you need to get as high a rho R as possible. That's as high as compression as possible. But as you go up in compression, as you increase your rho R, which would increase your fuel burnup fraction, instabilities take over and you hit a limit. And there's a fundamental limit that we've observed that's not predicted in the codes exactly, but it comes from us experimentally of these rho Rs. But this is what you'll think. The other way to increase rho R is make your system bigger. So at Examer, we're trying to go to a 10 megajoule laser. That will allow us to go to bigger targets, which will increase R, which should increase our fuel burnup fraction. So it's not just about density, it's about density and radius. You can also think about this in terms of the density and the confinement time. So if you can increase the confinement time, you can also burn which bigger systems, larger Rs, because it goes to the sound speed, R over the sound speed. Also, that's another way to think about this, increase the fuel burnup fraction. And roughly about somewhere around 30% to 40% is the maximum you can get, because as you burn the DT, let's say I burn 30% of the DT, well, that DT is no longer in your hotspot, right? Because now it's a neutron and an alpha particle. So I have halved my density just by the fact that I've burned up my fuel, right? So the cross section or your reaction rate starts to go down because your density is reduced because you've burned the fuel up. So there is kind of a limit of about 30 to 40%, which is practical for you to be able to get to as well. So this is just another term that you'll hear people in the inertial fusion energy sector talk about, because this is an efficiency metric, how efficient you are. Because if you can only burn 10% of your fuel with each shot, what you're going to have to do to compensate is you're going to have your rep rate, the number of times a second that you have to do this, go up. And right now we're talking about 10 times a second, but no one has demonstrated that yet, right? At Examer, we're trying to go bigger, and with the work that we're trying to do here, because if we go bigger and we burn up more fuel, we might only have to shoot once a second, which is actually more pragmatic, right? So that's another reason why this metric is kind of an important metric.
And John, I just want to let you know we're at the end of the hour. You're feel free to keep talking, but I just wanted to give you that heads up.
Nope, I am done. Like I said, I got to go back and work on this a little bit because there's a few rough spots still. But hopefully you were able to pick up enough from this that what I would say is right here, this power balance is a 1D rate equation. It's a necessary condition, but not sufficient, because the 3D effects are going to kill you. And the 3D stuff should be another talk about Rayleigh-Taylor and what kind of things happen here that we didn't have time today. But hopefully you got from this power balance what the basics are of getting into a fusion energy system, how you get the power out that you need, and how this tells you how you can compare magnetic confinement to inertial confinement. And that's it.
Well, thank you, John, so much for an excellent talk. Do you have time to take any questions from the audience? I know we're over the hour.
Yeah.
Great.
Yeah.
So I know there was one question posted in the chat. This was asked actually earlier. The initial hotspot fuel, is that usually from the gas and not the ice?
Yes, although as you come in, some of the ice layer does actually naturally from shocks and other things move into the initial hotspot. So the initial hotspot is about 50% of the original gas, and 50% is made up from the ice layer coming in. But still a much small. It's still only like less than 1% of the total fuel.
Well, I have a question as well. So with the Rise Hub, I know we're looking at polar like direct drive. So instead of like, I guess a complete uniform, we're just hitting the target directly on the two poles. Um, does that change anything? I know you had that comparison between direct drive and indirect drive. Does that polar like direct drive, method kind of change anything that you would present on or discuss about?
Yes. So in the polar direct drive, we only shine the lasers in from a certain fraction of the area on the top and the bottom of the capsule. And then what happens is the amount of laser energy that gets to your equator is often less. So you're trying to balance that. So what this will do is this will affect the symmetry of the implosion a little bit, right? It will not be completely round. It might have some polar shape to it or whatever, which basically means that you're going to have some 3D loss in what you're doing. And what we're trying to do is overcome that by making the system, the rho R, really large so that we can afford some of that loss, but still burn up the right amount of fuel, right? So all of this stuff is optimizing these things. So in that case, we're trading off rho R or the R and the energy in the hotspot with a little bit of a 3D loss. So with PDV work and hopefully alpha heating and things not being so bad, we'll be able to overcome this loss. So it's an optimization game.
I see. Thank you. Another question was posted asking why don't we use free electron lasers for direct drive methods?
If we had a laser, an X-ray laser, we would totally do direct drive with that. That would be the best. But the amount of energy in a free electron laser, I mean, it puts out picocoulombs of charge in the bunches of electrons. So it's just way too low amount of energy to be able to heat and ablate the material. But if you could get an X-ray laser, you would not need megajoules. You should be able to, like I said, NIF was able to ignite at 250 kilojoules. With an X-ray laser, you could probably play some games and you would only need a couple hundred kilojoules of laser energy to get this to work then. Versus a optical laser, which takes, because of the inefficiencies, 2 megajoules, right? So the X-ray laser would definitely win.
That would be awesome if we had one that could do that. I don't know if I'd want to work on it though. Are there any other questions right now? You can unmute and ask yourself too. Richard's just making a comment about LCLS and the X-ray laser that produces about 5 millijoule pulses. So yeah, we really would have to scale up a lot.
But you had the right idea.
Mm-hmm.
Whoever asked the question.
Well, let me stop the recording.